All right, welcome back, everyone. Today is lecture 12. Before we begin, I came across this issue on Submittee that many of you were not able to access Submittee. I'm not sure if that happened to everyone, but as far as like whatever information I've gathered, it happened, I think, because there was some feed that was broken, and most likely graduate students couldn't log in. I have added most of the grad students myself manually, but if you're still facing that issue, please feel free to send me an email and I can add you manually. So in case like whether you're a grad student or not, if you're not able to see the materials on Submittee, that means like you've been like kicked out of the registration section, and I can just go ahead and like quickly add you manually. So please make sure that you do that. Like just check if you're able to access. If not, just email me. Okay? So that's one announcement I had. The second announcement was about homeworks. So as you're aware, like homework 4 is coming this like is due this Friday. And then I'll release another homework, that's homework 5. And that is going to be the final homework. There have been like a few questions around it. And why is it like the final homework is because I'll give you like 3 weeks to work on that like final homework. And that will cover like a couple of topics. But then I want everybody to be like focusing in the last 3 weeks of the course. Everybody should be focusing on their final projects. And that's why I just like want the homeworks to be over like at least 3 weeks before we end the semester. So that's why like this homework is longer, of course, and you're given 3 weeks to finish that. It's another like project, obviously, but that is going to be the last homework because that question has come up multiple times. That's why I'm like answering that. Any questions about anything in general about the course or about the homeworks or? All right, and one additional thing, like with this homework 5, I'll also ask you to submit like your progress report for the project. And like, there is no need to like worry about it just yet, because as I said, I'll be releasing the homework this Friday and it won't be due until like 3 weeks from this Friday. So then that's a lot of time that you have. But just like wanted to give you a heads up on that. All right. So those are all the announcements. People who just joined in, especially people who are online, I just wanted to repeat. If you're not able to see the course or the materials on Submittee, it is because of some issue that came up, like I think yesterday. Just email me and I can add you manually to Submittee again. Okay, so if you face any issue, just like let me know. Okay, so let's begin. So in today's lecture, we are shifting gears a little bit. And we are talking about unsupervised learning because until now, as you've noticed, we've been like working with supervised learning problems, and we've worked with like data sets and with problems with models that have like some labeled data. And with our algorithm and with our models, we are trying to learn that, right? But now we are moving to unsupervised learning with the models being deep learning models. And the popularity of unsupervised learning is like huge in the deep learning area. Reason being a lot of issues, and one important issue is the availability of labeled data. Now, we've been looking at supervised learning in the past couple of weeks, right? And we know that these deep learning networks, be it a CNN, be it an RNN or a feed-forward network, it requires a lot of data. And if we are working with a supervised problem, then it requires a lot of labeled data, right? And when we were discussing CNNs, we came across this popular data set, that's the ImageNet data set that has like around 1 million images. And those are all labeled images. So they are like labeled into classes, different classes, around 1,000 classes. And believe it or not, these images are labeled by humans. So the cost of collecting this labeled data in itself is huge. And we would definitely like to use more of such data sets. But then there a lot of effort goes into that. And so we just don't, and if you also like, apart from like collecting data, if you look at this aspect of like the problems we are trying to solve, the real world problems that we are trying to solve, in many of the real world problems, you don't get labeled data. You don't get like the kind of data that these models require. And so obviously most of the real world, I wouldn't say like all of them, but many of the important real world problems are actually unsupervised learning. And so that's why we want to know what we can do with deep networks. How can we learn that? and maybe arrive at some conclusion. Because we have talked a little bit about unsupervised learning when we talked about k-nearest neighbors, and mostly those techniques were like around clustering things, categorizing things based on patterns. So what happens in deep learning is similar. We are going to pick that data and find some patterns, but we're going to also reproduce some things. So high level, the idea that I'm going to introduce today is different from what we've been looking at until now. And we'll continue our discussion of these kind of networks that are also known as like generative networks at times. And I'll give you a high level overview of what these look like. So for example, I have like some input data X, right? And then what we use is a neural network that we call an encoder. So what it does is it encodes this input in some ways. And that means like maybe the encoding could be like compressing the data, maybe getting some other representations of the data. I don't know. It's a very generic term. And we'll see that there are different models that do different things with this encoder thing, right? But regardless, I create create an encoder that creates another representation of my data, which is also known as the latent representation or hidden representation. Both are used equally in the literature, so you can like refer to them anything. And then using this latent representation of my input data, I can use a decoder, which is another neural network, to decode this X and then recreate this X in some ways, which is like X hat. So that's the kind of neural network that we are talking about when we talk about these kind of networks in unsupervised learning. So basically, I'm somehow trying to mimic this or like recreate this or reconstruct this. And one of the important applications you've seen with like this kind of a structure on the web, you've seen like this issue of fake images and fake videos, right? So instead of calling them fake, you can call them like reconstructed. So you feed some input and you can like literally create like human faces that don't exist. And so basically what you've done is you've reconstructed based off of some like input images that you fed to your encoder decoder. So these are the kind of models that we'll be looking at, and we'll begin with something that's known as an autoencoder. So that's like a part of this class of models, but we'll see like how is it like how it learns and how is it different from this one. All right, so high level idea of today's lecture is that we have an input and we have like these two units, encoder, decoder, and using these two units, we recreate the input. But obviously, the thing that must be coming to your mind is that I don't really want to memorize everything that's in my input, but because then what's the point of having this algorithm? I already have this data. And so that's the big question here, right? You don't want to recreate it, but you do want to learn enough so that you can recreate something else. All right, so that's that. Let's begin with what autoencoders are. So as I said, this is an unsupervised learning technique. Why? Because we do not have labels. I don't have any output. I just have my input. And I'm trying to learn something from that input. Let's say these are images. So I'm trying to learn some attributes from the images and get something out of it, right? So that's what it is. We use neural networks for this task. So this is like a deep learning paradigm, but it's used for like unsupervised learning, right? And it learns, like this autoencoder learns to like copy the input in some ways, and then like create another representation of that, and then get an output. So even before we jump into like the intricacy of what this is the input layer, this is known as the bottleneck layer, and this is the output. Let me just like quickly show you what exactly we are trying to do here. So for example, and I'm still like sticking to that encoder decoder type thing, right? So let's say I have like my latent representation or the hidden representation, and I will be like representing it with an H. And I have some input X. And I have some reconstructed output R, right? And just like any other learning problem, I'm like trying to uncover some function that relates X to H, and then some function that relates H to R. That's what I've been doing in all learning problems, right? So essentially, I have some function that maps X to H, right? And I have some function that G that maps H to R, right? And one way of thinking about it is that like this function that maps X to H. And obviously, because this is a deep network and we're using some deep network to like map it, this H, which is my latent variable, can be like written as, let's say I'm using like some non-linearity here, right? So it could be sigmoid, it could be ReLU, anything, and I'm denoting it by sigma. And I will have like W transpose X plus B, just like any other neural network. This is, let's say that's the function. So I will be learning the weights and the bias and everything, right? And then here, when I come to this part, unlike what we've been doing earlier, this reconstructed output, this R, is given by another nonlinearity. And I'm just like, just to differentiate it with this first one, I'm just like using this tilde or whatever you call it, this, I don't know, what is it called? This dash. And it could be the same, like it could be sigmoid or ReLU, right? And then another set of weights that are again different from this. But instead of X, I'll have my input as H, and then some B prime. Prime is a good, yeah. So then this differentiates it from these, right? So like one thing that I would like to point out here is that this reconstruction is actually this sigma prime, W prime, and then this H is this sigma W transpose X plus B prime, right? So that's exactly what's going on here. Is that like okay to everyone? Because I encoded and then I'm decoding, but for that decoding, I need the encoded input as well, right? So that's the like the math side of things. That's the function that I'm trying to learn. Now, a lot of like a couple of intricacies here. What is going to be my loss here, and how am I going to learn? Obviously, that's the big question, right? So loss is easy to understand. Like instead of like what we've been saying until now, y hat, and we had those y's, and we had some predicted y hats, and then we calculated the loss. In this case, it's going to be x and r. So this means that I'm going to penalize the difference between my input and my output, because I'm trying to recreate my input in some ways with that output, right? So high level, this can be written as, and this could be like depending on the type of problem we are solving. Let's say this is a regression problem. If it was a classification, then again we use the same idea that we've been using until now. So it could be like log loss, the negative of that, like the cross entropy. But here I'm just like thinking of this as a mean squared error. Let's keep it simple. So again, it's going to be the exact same thing that you've seen before. So x minus this r squared, and this r is exactly this expression here, right? So for the mean squared error. So again, loss is the same, but what we are trying to measure is the difference between my input and my reconstructed output. And again, depending on the problem, it could like be a lot of things, depending on like what it is. But the important point to remember is that instead of y hat, we are trying to find the loss between x and r, right? And r and x are related in some ways, as we've seen with these two equations. So that's exactly that's the fundamental idea of an autoencoder. It encodes, it literally encodes itself and then tries to produce itself. And then we try to compare the input data and then the output. And then we try to penalize that. Like if you're really far from your input, then obviously the loss is going to be higher and so on, right? And believe it or not, although we see these like so many like nodes in my output layer, but this is not much different from any feed-forward network in the sense that you can easily use backpropagation and gradient descent to train these models. So there is nothing new there except that the definition of my loss has changed, and so there will be slight changes in the way we are calculating the gradients. But like because we have added the nonlinear functions, so we can compute the gradients. And so this is like trained exactly in the same way, the basic autoencoder. Now, as I said, like the loss is essentially this input minus this output, and I'm trying to learn this. Now, this is like the very basic architecture of any autoencoder. And you must have noticed one thing, that I have this hidden layer, right? And I have like fewer number of nodes here as compared to like the input and the output, right? So the question arises, how are these helping me, right? And if are they helping me, first of all? And how are they helping me? So the fundamental idea is to have smaller number of nodes. And reason being that I am somehow trying to compress my input. What I'm trying to do is I'm trying to bring it down to a lower dimensional feature space. Because like if you look at it like one active, and these are activations, so that's why these are like denoted by these A's, right? So for every activation, I'm like putting together a number of nodes, and then maybe summing them up and passing them through a nonlinearity, I'm bringing them down to a lower dimensional space. And believe it or not, this is very similar to like principal component analysis, if you're familiar with that. Right. So what happens, like high level, if you're not familiar with that, that's also fine. What happens in PCA or principal component analysis is that you have this high dimensional data, and usually it's hard to work with that high dimensional data, right? Because of a lot of issues. And so what we try to do is there is like, what exactly are we trying to do with any learning algorithm? We are trying to uncover the variation in the data in some ways, right? We're trying to see what dimension is causing the most variance, because that will have the most impact on the output. So one clever thing to do, and let me write it down, because I think, let me quickly give you a high level overview of what PCA is, just in case you're not familiar. So in principal component analysis, let's say I have like some matrix A, that's my input, like matrix of like in my entire data, and this is high dimensional. So I can just like decompose it into something like this. You must have seen this equation. Again, there is no need to like worry if you haven't. So what we do is we decompose my matrix into like these components. And these are like the eigen, like if this is a square matrix, then these are like eigen decompositions. If this is like rectangular, then this is a singular value decomposition. Again, high level, the idea is that I figure out the eigenvalues and the eigenvectors of this somehow, right? By decomposing it into these components. And why are these important? Well, this is important because my eigenvalues, my eigenvectors give me the directions where there is most variance in my data, right? So I can rank them according to my eigenvalues. The vector that has the highest eigenvalue will be ranked the highest first, and then the second, and then the third. So what I'm going to get is like these eigenvectors, like a new basis, right? A new basis instead of like my original one. And why will this be helpful? Well, this will be helpful because let's say A had like, let's say this is 100 dimensional something, but then I figured that my data actually had variance across like only 3 eigenvectors. That was the most, like the 95% of variance was constrained within my first 3 eigenvectors. So I can just like come up with this new basis, and I can like have my data represented in these 3, along these 3 features. So again, there is no need to like get, there is no need to get intimidated by like all these terms. High level, what's happening is I have shrunk my data to a lower dimensional space by calculating the eigenvectors and the eigenvalues. Because what these two are doing is they are telling me what is the direction of the most variance. And then what is the most variance? So that's my first eigenvector. And then what is the direction of the next most variance? So that's the second eigenvector, and so on. Right? So we can actually figure that out by doing this decomposition, high level. So as long as you know that this is what PCA does, right, we can shrink our data into this lower dimensional space. That's exactly what autoencoders are doing. If you think about this, like I have like this input x1, x2, x3, and so on, and all of them are like, we are trying to compress them in this bottleneck layer. Bottleneck layer or latent space or hidden layer, you can call it anything. All 3 are fine. And so what's going on here is that if I just sum these up, instead of like, let's say I don't do this. Okay, let me show you. So let's say I'm just like summing these up here, right? And then I also perform some nonlinearity here. That's what we do in nodes, right? So like if we forget about the nonlinearity and just like the summing up, in some ways, we are bringing our data down to that like basis where the PCA can be found in some ways. So that's what we are doing here. In PCA, we did the reverse, like we came down, like using the data, we came down to that space. We can come down to that space just like by using fewer number of nodes. That's like once you start training this, that's where you're going to end up. So that's a good thing in some ways because I have reduced my dimensions and I've extracted only the useful information from my data. And now another added good thing with this autoencoder is that in addition to the summation, I will have the non-linearity, right? That's what we do in nodes. And so believe it or not, these autoencoders are able to learn non-linear functions within that lower dimensional space, which is like a huge plus in terms of learning. So you are in a lower dimensional space and you're still able to learn like very, I would say, detailed intricacies of the data, because I'm applying this is like one level ahead of like what we do in PCA. So in all ways, like if we have fewer number of nodes, we are able to bring down my dimensionality of my data to a lower dimensional space. And so very first, like if you look at the historic, the history of autoencoders, they were actually used for dimensionality reduction mostly. They were used for dimensionality reduction initially. Now we've started using it for other applications, as we'll see today, right? So that's the idea why we can use it for dimensionality reduction. That's the first thing. And okay, let me see if I missed anything. Yeah, I think I've covered the fundamental idea. So mostly in any basic autoencoder, you will have a less number of nodes here, not just for dimensionality reduction, but also for the fact that I'm trying to learn something from this data, but I'm trying to learn only the important things from this data and not like memorize it. Because if I exactly use like the exact number of nodes as my input, I might end up learning the identity matrix or the right. I mean, if you might, right? And so so I don't want to do that, right? Of course I want to copy, but then I want to generalize, because the whole point of learning is that, of course, I trained it on this input, right? And then I would apply it to some other input, some other data. And that's another like second reason for having smaller, lower number of nodes, is because I want to learn only the important features that would be significant enough to generalize. And so that's the second reason why we, in the bottleneck layer, we lower down the number of nodes. And of course, it's a hyperparameter depending on the problem. We might use like some number of nodes or like really small number of nodes and so on. Again, depends on the problem and domain knowledge. Okay. Okay, so another aspect of this, and like we are looking at a very shallow network right now. And so the other thing that might be coming to your mind is like, how about I add another like bottleneck layer and another bottleneck layer and so on, and then do a similar thing for the decoder as well, right? So this part is the encoder and this part is the decoder. So always remember, like this bottleneck separates the encoder and the decoder. So how about I add like more layers here? So what has been found is that if you make this network like really deep, again, it memorizes the input because you're giving it enough power to keep going and like keep applying all the intricacies, all the non-linearities, and like just copy the input to the output, which is good in terms of training. But then we all know, with like having worked on so many projects, we don't want it to overfit. We don't want it to memorize this, right? So two things, as I said, if we have like this, the number of nodes here, like that are equal to my input, or we have a deeper network, that might lead to overfitting. So those are the two issues that we are going to address today. But let me show you some different types of autoencoders. And okay, yeah. So in this section, I'm talking about like what major tasks they've been used for. So information retrieval, dimensionality reduction. Information retrieval has been an important aspect of autoencoders, specifically in like in databases where it's hard to get like query related information. Autoencoders are able to do that because like they can do very well with the replication, right? So if you give them something, they can replicate that. So that's that. Yeah. Okay, yeah, so an ideal, so this is also important. Yeah, that's what I was talking about. So an ideal autoencoder should balance these two things. It should be sensitive enough for my inputs so that it does learn something from those inputs, right? But it should be insensitive to some of the important details of those inputs so that it does not memorize my inputs. So there has to be a trade-off between both of them. And then it goes back to our bias variance trade-off type of thing, overfitting, underfitting. So this can be thought of as like a similar kind of idea. And of course, believe it or not, we use regularization to deal with that, right? So we'll see how we apply that to autoencoders. But the very first type of autoencoder that we're looking at is known as the undercomplete autoencoder. So what exactly is that? It is exactly this thing, this one. And this is known as undercomplete when the number of nodes that you're using in this like bottleneck layer, it's less than the number of input nodes that you have, right? So whenever the number of nodes are less than the input, then it's an under complete autoencoder. And why are we doing that? We already discussed that. We are using that for dimensionality reduction. We want the model to learn only the salient features, the significant features, and not memorize. So this is known as the undercomplete autoencoder, and it's a deterministic model in a lot of sense that, and we'll see like what stochastic models are. So let's not go there. And yeah, again, some of the issues with undercomplete autoencoder is that we don't have any explicit regularization term. If I just go on if I go on increasing the nodes, and if I go on making the network deep, then like the issue of overfitting will come in again in this undercomplete autoencoder. So obviously, just like before, we have a solution to overfitting, and we are very much familiar with that solution of overfitting. That's regularization. So we use a lot of regularization in autoencoders to get rid of this issue of like when like you have a more number of nodes or you have a deeper network, what should we do? So the way this regularization works in autoencoders, and let me see. Okay, yeah. So this one talks about the two issues that I figured that I pointed out earlier, right? Autoencoders fail to learn anything useful if encoder decoder are given too much capacity that both the networks are really deep, right? The second thing is like there is this case of overcomplete autoencoders. So overcomplete is just the opposite of undercomplete in the sense that I'm providing more number of nodes here, almost equal to the input or sometimes even more than the input, right? And then with the idea that like, I want to learn more. Maybe the images were so intricate and so difficult to learn that I want like more nodes here. So obviously with the undercomplete architecture, you don't want to do that because that might lead to overfitting. But with regularization, you can do that. So with regularization, you can have a deep autoencoder network and you can have like an overcomplete network. And a small amount of regularization is going to do something that is going to create a network that's known as like a sparse encoder network. So let me see if I missed anything. Yeah, so what this section talks about is that we don't want to like limit our model capacity. We want it to learn more, but then we don't want it to overfit. And so just like what we did with like earlier models, like other models that we've talked about before, if we add some kind of a regularizer, that is going to put a penalty on my learning process, right? If I go beyond something, then that's going to stop my learning. And if you remember from the definition of regularization in general terms for any machine learning problem, we put that penalty on the weights of my learning process. If you remember, right? So we used to penalize weights that if weights go beyond some like constraint, then just go and penalize it. And then that could be like in terms of the squared, so it could be L1 regularization or L2 regularization, but we were penalizing weights. So now I want everybody to like pay real like attention to sparse autoencoders because these are different in the sense that we are not putting this regularization on my weights. I'm putting this regularization on my activations or my hidden layer or my latent layer, right? So let's say like we are in these sparse autoencoders. So these are known as sparse autoencoders that have added this like regularization to my loss, right? And let me actually write it down before we move on. So in addition to like, if you remember from earlier, right? So in addition to X and R, X is like my input, R is my reconstructed output, right? I'm putting another function, which is a function of H. That's my hidden layer, and that's my latent layer. And no more of, so in earlier models, this thing used to be a function of the weights. So that's not a function of the weights. And so what we'll do is, right, we don't want our model to learn the identity function, right? So what we'll do is we'll penalize our model based on some activation value, based on some value in my like activation layer, right? So let's see what that does. Now we'll construct our loss function such that we are able to penalize this H. And what will it do is that like visualizing will make it better. So this is what will happen, right? So this is my encoder, this is my decoder, right? And this is my latent or bottleneck or like hidden layer, right? And because I've applied that regularizer to my loss, right? I'm somehow doing some kind of a switching on and off to these activations instead of doing something to my weights. Remember in the regularization, we were restricting the weights, making them 0 in my original like machine learning definition of regularization. But that's not what we're doing here. We are like trying to turn on and off like these values. For example, in this network, this dark yellow refers to like yes activation, and this like light yellow refers to no activation here. So that means like not any information passes through those nodes. And so I am allowing more like nodes in my hidden layer. I am allowing deeper networks so that I can learn the best I can based on my capacity. But then I'm also restricting these activations to a certain extent so that my encoder to decoder doesn't result in like an identity function. Okay, so this is important to understand because this penalty that I put on my loss, it encourages like the model to activate based on like what my inputs are coming like to that activation. There are 2 different types of activations that are used, and we will go into the details of both of them. So let me write them here. And I have like listed them here, but let me show you what exactly these are. The first one is something that you're familiar with, L1 regularization, but let's like quickly review that. Okay, so let us assume, and I'm like going by this picture here. So the loss is L x hat, where x is my input, x hat is my output. Plus you will have this extra term, and this is L1 regularization. Okay. So what you'll do is you'll have like this sum of all these i's. So I is the observation. So for any is observation, I'm going to sum them up because all of them are being summed up on that node, right? So that's what this is referring to. And A is for activation for that. And obviously it's a function of weights. And you do add the regularization constant that was there earlier in other problems as well. This is like for the fine tuning of like how much regularization you want, right? So this is very similar to what we have seen before, L1 regularization, that you're penalizing based on, you're penalizing the activations in some ways. And then obviously it depends on us because this is going to be an input parameter. How much do we want to penalize? So you can fine tune your model in some, right? So this is exactly what used to be L1 regularization in like earlier models, except that instead of like the weights, I have like these activations that are being penalized when we are like minimizing the loss, right? So my new loss is this. Okay, the second type of loss that we use in autoencoders, and this is important to understand because when we start talking about stochastic autoencoders, you will see that that's the loss that will be used, right? So that's important. I know everybody is familiar with L1 and L2 regularization. So let's talk about the second one that's known as the KL divergence. And this is the second form of regularization that's used in autoencoders. Let's try to understand what this is. So generally speaking, KL divergence is a technique where you can figure out the difference between 2 probability distributions. So that's helpful in our case because we can define, so in this case, you might not see the entire benefit of why we are using KL divergence, but you'll see that when we use stochastic encoders. But for now, just think that this is some way of like defining the difference between 2 probability distributions or 2 stochastic values. That's enough for now, right? And you know that this like activation is a kind of a Bernoulli random variable because it's like either a 0 or a 1, a 0 or a 1. So based on that, you can assume some form of distribution that it has. And based on that, you can find the difference between the distribution that your model learns versus the distribution that you decided it should have, right? And so penalize the moment it goes away from that. So for example, let's say I decided some parameter, and there is a parameter that will be defined here that's known as the sparsity parameter, right? So it is defined, it is denoted as rho. And let's say I define this sparsity parameter to be 0.2. It's some like value. And then you can calculate the sparsity parameter for every node using your data. So if you see that that sparsity parameter that you calculated using your data versus the one that you've set for your model, they are like really far apart, then you're going to like turn off that node because you say that these are like really far apart. There is a huge divergence. And then if they're like really close enough, and then obviously we decide how close is close enough. Let's say I decided if they are more than like 0.3 apart, then I'm just going to penalize the model. If they are less than 0.3 apart, then I'm going to say, okay, that's fine. Let's take it. Let's keep it on. So that kind of an idea. Right? Okay, let me write down the equations and maybe things will become clear to everyone I'm talking about. So the thing that we are going to estimate or calculate is this rho sub j. And j is referring to a particular jth node in my hidden layer. Okay? And I'll put a hat because we are computing it or estimating it. And then let's say I have like m number of observations. So for every node, I'm going to sum those like inputs in some ways, right? And so summation over all i's, and this stays the same. AI for the hidden layer, and x is my input. And if there's a deeper network, then like it depends like the input from the previous layer, right? But I'm just assuming there is one. So m is the number of training examples, and then this is the input value x that triggered this activation A, right? So this is how we define this sparsity parameter. This is how we estimate our sparsity parameter for every node. So we have rho sub j, we have rho, right? Now comes like, when do we penalize our model? Well, we penalize our model with something like this. There's like, this is my loss. This is my final loss now. It's going to be L x hat as usual. And then this regularization term, which is a function of, and this is also known as I said, the KL divergence. KL is nothing but a function summed for all values. And this. Okay, I will talk about what this is, but for now, just think that this is a function that is somehow measuring the distance between my sparsity parameter that I decided for my model and my rho sub j hat, which I'm going to estimate from my data. So it's very similar to, I would say, like a cosine similarity, or like some similarity that some distance measure that we decide. But it has a stochastic nature to it. And this will become clear, as I said, when we talk about stochastic models. But this is another way of like regularizing my autoencoders. So I have a formula for this one, so maybe that will make things clear. Any questions so far before we move on? Yes.
I'm a bit unclear about what the sparsity parameter is representing exactly. So AI is the
activation for yes. Yeah, so no, I can explain that. So what we are trying to do is we are trying to make our model sparse. And I'm trying to make my model sparse by activating only fewer nodes as compared to what I have in my hidden layer. In order to do that, I have to have some criteria. And the criteria I created is based off of this sparsity parameter. Maybe I got this information from some like domain knowledge or from somebody else like knowing about the problem. And I set it to this. So maybe think of this sparsity parameter as a threshold. And so if I'm like really away from the threshold, from the like, I'll have a calculated value of the sparsity parameter as well for every node based on like my data. Because like this is important. The thing that I'm calculating is important because maybe that node has some information that's like is getting some information that's really useful. So I don't want to lose it. And so obviously when I do this kind of a calculation, that's going to come up there. And in some ways, if like from the problem, I know that the sparsity has to be 0.2 and I'm going to extract most features if sparsity is closer to 0.2. And most likely, if that's the case, then this like calculated value will come close to that. And so I will penalize that model less or that node less. And so that will be activated. But if for some reason I see that this like this thing is like really far apart from 0.2, then maybe depending on my problem, because I got this 0.2 from my problem, right, from some domain knowledge. So maybe like this is not doing enough. This node activation is not enough. It's not getting enough information. And so it's like really far apart from that. And so there is no need to like keep that on, if that makes sense. Yeah. Yeah, and I have like the paper that talks about that, so you can go into the details. But the fundamental idea is that we are penalizing the like how much this calculated rho sub j is deviating from my rho. That's what we are penalizing here in this scale. And let me quickly write down what this is. So maybe that would give you a better idea of what the way we calculate this KL, summation KLJ is the summation for all nodes. And then this is the sparsity parameter that I came up with, log, well, this should be hat, 1 minus rho. And of course, you don't have to remember that. But again, this is like a distance measure between rho and rho j. And we are penalizing the models that are really far apart from each other, because like thinking about this sparsity parameter as something that has like that has all the sparsity parameter that we decided to have for a model is most likely the best that's there for that problem. And if I'm deviating too much from that, then I don't need that activation anymore because it's not enough information in that sense. Right? So this is the KL divergence is the second kind of regularization that we used with autoencoders. And the scale divergence is really powerful in the sense that it creates a sparse network, like some of the nodes are activated, some are not, but I can still go ahead with a deeper network with these like sparse nodes. And if you remember, we've seen this kind of a thing before. Remember in deep networks, when there is a trick that we apply and then that avoids overfitting, where you can drop some nodes and then like not exactly the same, but similar in the sense that we dropped some nodes and then connected from the previous layer and skip one and go to the next and so on. So that also avoids overfitting in some ways, right? So that's in some ways we're doing similar, but we are adding a regularizer that's like doing that for us. It's creating a sparse network. Bless you. All right. Questions, doubts, people who are online. I always forget to ask you. Yeah, okay, so that's what sparse autoencoders are. They have a, like one easy way to remember these sparse autoencoders is that they just have like this regularization term added. And this is the KL divergence regularizer. And so it just like drops off many nodes or many activations. And I think this is a nice article that, okay, this was just a Wikipedia article, I thought. Okay, yeah, maybe I have it in the references, but we can go over that later. So, all right, the other type of autoencoders that we'll be looking at today are known as the denoising autoencoders. And again, the fundamental idea for even the denoising autoencoder stays the same. If you like remember what we are doing is like we have the loss of like X and X bar. And let me show you what I'm saying. You can come back here. So usually like what we've been doing is we have like X. And then remember the thing that I was drawing earlier? This is H, this is an F and G and R. So what we're doing is we are getting G of F of X, and that's the loss that we are like learning. And we are penalizing, like this loss actually means that we are penalizing if this is like too much dissimilar from this, right? And we also saw that there is this issue that if G has the capacity, meaning if it's deep enough, or if we have nodes like that are like more than the input, then most likely I'm going to copy my input as it is to my output. And that was an issue, and so we introduced this regularizer, right? Now, the other thing that we can do, and that's what this denoising autoencoder or DAE does, is that we are not going to like have the loss function defined like this, but we'll have a loss of something like G of F of X tilde in that. And so what is this like X tilde? Well, this is like a copy of my X such that I have added some kind of like, I've corrupted the input in some ways. So let me show you what I mean. Because remember, in any learning problem, I want my network to learn but just enough so that it does not like overlearn or it doesn't overfit. So in order to deal with that, this is the entire process. So I have like this input, let's say digit 7 from MNIST. And what I did is I purposely like added noise to my input image, right? So I corrupted it in some ways. I made it like a poorer quality image, right? And then I feed this corrupted input into my autoencoder so that it picks, like I did that purposely so that it picks like the important features from my input and not like overlearn the input. Although the original input is this, right? But because I have added noise, most likely if it's a good like configuration, it should not like learn noise. And so the way this will be set up is that I'll have like these outputs, right? And then going back to the loss function that I just defined, I will be comparing this output with my original image. That's why like in the loss, you have X and then X, the f of X is calculated on the X tilde and not X. So again, like if you're not fully understanding this, this is my X. This is my X tilde with the corrupted thing, right? And the output that I'm going to get here is going to be something like a function g of f of x tilde and not f of x. But the loss will be like computed based on like these two values, x and g f of x tilde. That's a fundamental idea here. So again, in some ways, like implicitly, we are regularizing in the sense that we are trying to give it something, some input that's pretty similar to my input, but not quite, because I'm like explicitly adding this like noise to my my inputs, my input images. And again, this technique is known to have worked like really well with image data sets, with sound data sets, and similar like problems. So this is known as the denoising autoencoder or the DAEs. All right, so that's that. The last part of today's lecture is actually stochastic encoders and decoders. And these are slightly like more, I would say, difficult to visualize, but we'll try to do that like, and we'll try to like break this up into smaller parts and then we'll see what goes on. So until now, what we've seen, like all these three models, these are deterministic models. These are deterministic autoencoders, right? And now we are going to look at the stochastic side of things. And there are more stochastic autoencoders, by the way. This is just one of them. Okay, and we'll see more on Friday, most likely. But the fundamental idea here is that we are trying to, like until now in like any deterministic model, we are trying to learn these like specific points or specific data points, right? We don't want to do that anymore. Rather, we want to learn some probability distribution of my input. That's what makes them stochastic. But before we jump into this, I quickly wanted to go over like this thing, the TensorFlow introduction to autoencoders. This actually shows us a very nice implementation of three different deterministic models. I've provided the link in the lecture notes at the bottom, so you can go and check it yourself. So what it does is it's using this fashion MNIST data. I don't know if you're familiar with that or not. It has like pictures of these different items from some fashion outlet. And notice like this is the basic autoencoder, and this is like the deterministic one. And we have like these inputs. Like look at the top row. That's my original images. And then this is the autoencoder with just like two dense layers that has produced like similar output. So you can see how close, like, so this is the reconstructed output, which is pretty good given that this is just like the basic autoencoder. And then what they do is like, and very easy to implement, you can specify the latent dimensions. So that's the H that you're specifying. So that's the only thing that you change because the rest of it is already given. And you can like go ahead and do some experimentation with that. Notice that they are training it with the gradient descent, the same algorithms, Adams optimizer here. So you're all familiar with that. As I said, the basic autoencoders along even with the regularizer, you train them as you've been training all your feed-forward networks. So the training part is the same. And okay, let me just skip that. The second one that they were showing, oh, this one is denoising or this one is, I'm not 100% sure. I think this is the denoise because like we have the noise given, right? So here is like the second example. That was the basic autoencoder. Look at this one. Like, so I have the original image, right? And I've added some noise to that. So I've added like some noise to the input here, right? And then what this denoising autoencoder is going to do is going to learn using that input with like noise in it. And notice like the output, which is like, as far as the quality is concerned, I would say this is like better as compared to my basic autoencoder, right? If you just look at the, can we just close that window? Thank you. Yeah, just focus on the two rows, like the second row in both of these sets, right? If you look at the top one and you look at the bottom one, like let's say we are looking at this particular image, it's better, I would say, but like as created by the denoising autoencoder as compared to the original one. Because like denoising autoencoders are shown produce better quality output because in some ways they don't memorize the input. They have like they try to filter out that noise and in the process they learn important features from the input. So that's the second variant of the autoencoder. And then the final one, I think, is showing us as far as okay, so that's anomaly detection. We haven't talked about that yet. That's another important application of autoencoders that they can detect anomalies in the data set. Because we haven't talked about that yet, so I'll just like leave it at that. But my recommendation would be to go to this like tutorial and just see how you can implement autoencoders, because sometimes they work as like base models for your other models that you're trying to implement. Let's say you wanted to do dimensionality reduction. Let's say you wanted to remove noise from your data. And I think like recommender systems are a good example of like why we need autoencoders before we actually implement the actual like model. So we'll see all of that. There's a paper that I'll be looking at the end. But let's go back to the variational autoencoders or stochastic autoencoders. And should we take a break quickly, 5 minutes, and then come back? Because I think that's a good logical break here. And then let's talk about it. Yeah, sure. Okay, let's get back to variational autoencoders. And as I said, like these belong to another family of autoencoders that's like based on uh, getting or extracting the stochastic nature of like encoding versus decoding. So that means we are trying to do some kind of a stochastic sampling operation with which we are going to create new data points. Because if you think about like what we are trying to do when we said we have like some input X and then we have some output X, of course, I'm trying to reconstruct my input. But then based off of some like important input information, I also want to create something new there. And that could be easily done if instead of getting deterministic outcomes in my latent space, I'm looking for some probabilistic outcomes, or if I'm looking for probability distributions rather, right? So this one here, like this particular image, we just have this one. It shows us like what a deterministic autoencoder does. For example, like you have an input, then you have an encoder, you have some latent space, which in this case is sometimes referred to like it's denoted by Z or by H. Like in some papers, you'll see it denoted by Z, but we are denoting it by H, so let's do that. Now, what we're doing in a variational autoencoder is that we are like what you're trying to learn is a completely different mathematical function. We are trying to learn probabilities. Okay. So what is the role of this encoder here? My encoder is going to compute the probability and some probability, let's say it's denoted by phi, and that's the probability of my H given X. That's the probability distribution that my encoder is going to learn. And then I have some representation H or Z, whatever you like to call it. And then using that, my decoder is going to decode that. And the way it's going to decode that, it's like maybe sample from that distribution and then reproduce some kind of a distribution, right? And that would be some, let's say, instead of P, let me write a skew of theta. And then that's going to be some X prime H, right? Based off of like my input H. So that's like high level what these variational autoencoders do, that you have some input, right? And then instead of like learning the exact points from my input, you try to learn the probability distribution of the input. And the whole point of doing that is that like the advantages of doing that is first, you'll get a more smoother representation of the output because you're not just like basing your outcomes or your outputs on some like deterministic points, but on the whole probability distribution of your input. And then because you're sampling from that input, because you'll have like some latent representation, like your encoder will create a probability distribution, right? So my encoder has created this. And I'm going to sample from this to get some outcome probability distribution. So most likely I can have new points and I'll have a better representation of my input as compared to what I have when I had like deterministic values. So that's what we are doing. And like to be very specific, we like to parameterize this, like have a parametric like way of defining my distribution. For example, it could be a normal distribution. It could be like any distribution that is defined by some parameters. And so we will be learning those parameters. And like if you think about like any usual distribution, any usual probability distribution, the way we define that is by using the mean and the standard deviation, right? If you have that information, most likely you know like almost everything about that distribution, right? So you're trying to learn those vectors, the mean and the, so let me just like add it here. So you are actually trying to get the mean from the input and you're trying to get the standard deviation from the input. And these are going to be like some vectors and then use them as like inputs to get like this final encoder output. Right? So it's the like we learn a mean and standard deviation vectors like with desirable like which describe the probability distribution of my latent space, right? And then yes, go ahead. Yes, yeah. So that's a good question. Yeah, we need the entire data set to finally get the final Z, the probability of this Z or H. Yes, that's a lot and that's bad. But yeah, you will see that there are advantages, and also like not just that. Think about back propagations. There is a negative side to that. Like you have these probability values, so these are like stochastic values, and when we think about back propagation, we need to have the derivatives, and then we need to propagate those derivatives. And that's like these things are going to block the derivatives in some ways, because like you cannot, because of the stochastic nature of like my latent space or my H or my Z, how will we backpropagate? So those are some of the issues, of course, but let's first try to understand how this, like the forward step works in, and then we'll come back to the backpropagation and other things. All right. So as I said, H is my latent variable. And first, let's try to understand what is the loss before we talk about the backpropagation. What is the, like, how is the loss defined in this one? Well, the loss is like a function of a lot of things. The first one, that's my phi, and then the theta, and then the x, right? Because I derive the distribution based on my x. That's my input, right? And of course, this is equal to the reconstruction error. And we need the regularization term here always. So it is defined like that. So let's see what this reconstruction term is. And this is the expected value of the log likelihood, the negative of the expected value of the log likelihood. Let's assume that we're doing some classification problem. So instead of like having the exact, like the negative of the log likelihood, I'll have the expected value of that, because we are talking about distributions now, right? So to be very specific, I'll have the negative of this, and this is like the subscript. Let me see if I'm able to write it here. And remember, this was H given Xi, right? And then this is log. So this is something that we have seen before, but instead of like having the actual Y or Y hat, you will have the probability phi H Xi. And I is referring to like one training example. So in some ways, like you'll have to sum them up to get the final cost function, just like you do always. But this is just like the loss for one value, right? And then you'll have the regularization term, which is important. And we're going to jump to that now. But this is just to show you that this is the loss value, which is the expectation of this probability that you're learning. Okay. So having said that, why is this regularization important? That regularization term is important. That like we just generally said that we are learning this probability distribution from my input, but then like your output could be anything depending on the way your like learning problem is set up, and it can go like really wild, I would say, right? So the way we try to control that, right? The way we try to control that is by using this regularization term. And what this regularization term is going to do is like, first of all, we want some smoother representation of my input, right? I don't want like it to have like some clustered output somewhere. And so that's one problem that might come up. Or we can have like discrete outputs. That's something that we don't want. So in order to deal with that, we have this regularization term. And the regularization term is actually coming from the KL divergence rule that we talked about earlier. And let's see how that helps us. Well, that helps us because I can decide a prior. For example, depending on the problem that I'm solving, let's say I usually, in most problems, we decide that my prior distribution is my normal distribution, a standard normal. And the regularization term is going to penalize if I'm too much away from that distribution. So that's how this regularization term helps. And then maybe going back to your question, that's like, if we are looking at the entire data set and then we're just like saying derive the distribution, then it could like be anything, right? So what we do is we have some prior, depending on my, let's say, some domain knowledge I have. And then I set that prior and then include the KL divergence as my regularizer. And so that's going to penalize the model if I fall too much away from a standard normal. Let me write it down, then that will make things clear. Okay, so the loss function is clear to everyone. And this is a more generic form of the KL divergence here. And because it's a distance measure, so we sometimes denote it with D, like some of the papers call it D. Sometimes you'll see KL. That's the same thing. High level, what you need to remember is that whenever we are talking about KL divergence, we are talking about the difference in probabilities, in probability distribution values, right? We're not talking about deterministic differences like in cosine similarity or in like other types of Euclidean and other distances that you're measuring. This is also a distance measure, but distance between probability distributions. That's the only thing that you need to remember here. So as I said, And remember in the KL divergence, I said like the difference between rho and some like rho hat or something, right? So similar to that, I'll have like some prior, and I am just like denoting it by P of H because that prior is um, established for my latent layer with my hidden layer, right? And usually it's a standard normal because like from a lot of experimentation, people have arrived at this that this like works really well for most problems. So this is like a normal distribution, obviously with a mean of 0, standard deviation of 1, as like you all are aware of. So that's a normal Gaussian or a standard normal. And that's a common choice of prior. But then I'm not saying that other distributions cannot be used. Of course, they can be used depending on the problem. But for most cases, this is the prior. All right, so that's good. Now, the other thing is the inferred latent distribution, which is not fixed, which is like something that we are inferring from my input data, right? So that's there. And that is something that I'm going to put here. So P of P that we just, that's the output that my encoder is going to produce, right? So this is also known as the inferred latent distribution. And this is my prior that I put on my latent distribution. Now this term is going to be added to my loss, right? So I have the reconstruction term that was the expected negative log likelihood, right, of my encoder output, plus this divergence, this distance measure, right? So whenever like I have some output that like deviates a lot from the standard normal, then this is going to penalize the model and not let it go beyond that. So like some of the advantages of using this is that it's going to encourage my encodings to distribute evenly because of like this prior being standard normal. And then you won't get those clusters in your output, which might be possible in a lot of cases. You'll get a more smooth output and a better representation of your input, right? So again, let me summarize. I'm getting the input data, extracting some kind of probability distribution of my input, right? And then getting it into my latent space. And then I'm sampling from that latent space and then producing some probability distribution. And then that's the entire like forward layer, right? We are coming to the back propagation because then that has issues. Yeah, you had a question, Stephen. So you're saying like X prime versus X?
Yeah. Wait, so we do forward propagation up into the latent space to calculate the distribution, right?
Yes.
And then you take a sample from that distribution.
Yes.
Forward propagation with that sample.
Yes. Yes.
So what is that sample compared against?
Yeah, so this sample is still compared against my input sample.
How does that?
So yeah, that I'm coming to that actually because like if you're thinking about the loss being like how you compute the derivatives and how you come back, then there's a trick to that that's known as reparametrization because you cannot directly do that. You have two different probability distributions. That's what I think you're pointing out. So how will you like back propagate and see how different they are, right? Is that what your question is? Okay, if you're thinking about this, if you're specifically talking about the reconstruction loss, then that's the log likelihood that I talked about. Or so it's still like you have the expected value of the latent space and then the log likelihood of like this probability distribution, if that's what you're talking about. Because like this is just the regularization term. So if you're talking about the LX X hat or X prime, this part, the first part, was actually the expected value of the for the latent, the expected value for the latent space, and that's a negative of the log likelihood of the expectation of that. So we'll have to take the expected value, like the probability distribution doesn't have like a discrete value as such, if that makes sense. And then yeah, that comes back to like how to train the network because the output is a result of stochastic sampling. And so I don't have like some, of course, like I can find some expectation around that probability, but then how do I back propagate the gradients? And first of all, how do I calculate the gradients for these probability distributions? So those are some of the issues that like we're going to address just now. And there's a trick to like how you do that. But yeah, that's the loss is going to be a sum of like this term plus like, as I said, the expectation of the negative um, log likelihood of like my this P of phi h given x. That makes sense. Yeah. Okay. So here is like this summarizes like what exactly we're doing. So first the input is encoded as a distribution over the latent space. Then a point from the latent space is sampled from that distribution. And then the sample point is decoded, reconstruction error is computed, and then like the reconstruction is back propagated through the network. Now the question arises like, how do we back propagate through this stochastic network, right? And so the way we do that is known as reparametrizing. And how we do that is like the key idea is like you'll consider some latent vector h as like a sum of some fixed mean and some fixed sigma. And that sigma is like standard deviation, obviously. That is scaled by a parameter epsilon. And that epsilon is supposed to be drawn from some like known distribution. So you have created like, I'm going to write that down. I know that's a lot of information, but I'm just like giving you a high level idea of like we redefine the latent space in some ways to make it differentiable. Because like right now it's like a probability distribution. And so like in backpropagation and in gradient descent type techniques, we need the derivative of the loss with respect to all the parameters that I have, and then only I can backpropagate. And so that's what like reparametrization does. That's what it helps us with. So I'm going to like redefine my h in some ways. If that makes sense. Okay, let me write it down. Then maybe that will make sense. So you write down the key idea. Okay, so because we cannot perform backpropagation as it is, so I'm going to do something. The key idea here is that this H, it belongs to some normal distribution with some mu and sigma squared, right? And what we'll do is we'll have some fixed vector mu and some fixed vector sigma squared that defines some known distribution or something. That's a normal distribution. And then this will be scaled by an epsilon, right? That is drawn from a prior distribution. So like in some ways we have like, of course, there is stochasticity in the way like we're doing encoding and decoding, but in some ways we have made it like deterministic. For example, now my H, instead of like being a probability distribution and we are saying like this is like getting the expected value from that probability distribution, let me just like do something like this. So basically I'll have like this scaled by this epsilon, right? And like, I'm going to show you what this does. Like, how is it different from like what we have? There's a nice picture in one of the articles that actually talks about like how this particular thing helps. So how this helps is that, let's say I had something like this. And of course, we are going to go into the actual paper, but I'll still show you how this helps. And I hope I'm able to draw this thing. So this is my H. This is my X, right? And this is the final function that I'm learning. My loss will be calculated here and I have to backpropagate. Now, but in addition to whatever I have added like this. This is my P, that was my distribution in of my latent space. And let's say I have like this epsilon from some prior distribution that's like a normal, standard normal. And finally, my H is going to be some G, which is a function of X and epsilon, instead of being like a probability distribution. That's high level what we have done. So like high level, what we've done is like, instead of like this being a probability distribution, deriving some ideas from some known distributions, I have defined it like, or redefined it as a function. If that makes sense. Let me show you the actual picture. And so we can back propagate because like this is a function. This is an article that you. Where is it? Let me see this one. Yeah, this one I think shows this picture and better drawn here. Okay, this is all of this we already discussed. The reparameterization is okay, that's okay, that's strange. I clearly remember I had a nice picture of like that reparameterization. Maybe it's here. I don't think this one has, but yeah. No, this one doesn't have. I'm sorry about this, but it's a nice demonstration of like how they are different. Don't think this one talks about it. That is in fact strange. Let me just here. Okay, this is like, I'm sorry about this, but like what exactly those two pictures show is that initially we did not have the two inputs like the other epsilon input that I was just showing you. And so what we can do here is that, let me just repeat this thing again. Like in back propagation, because now my H is no more just like a probability distribution, but I've like reparameterized it in the sense that I do get the probability input, which is like phi, and I also get like my X and my epsilon. And so I have like this new function that's defined, and then I get like my F. And because this H is now a function, not just like a probability distribution, I can get this value here. That was the fundamental idea that they were from. Earlier, we did not have this. And so I was like, my H was a probability distribution. So that's like, there was a nice picture in like one of the articles that I'm unfortunately not able to find out, but they like show the difference between like what's going on. Right, so you can back propagate this, and then you can compute like based on this H, and then the chain rule, you can compute like some derivative with respect to phi as well, because now you've like redefined your H as being a function rather than being a probability distribution. So that's the fundamental idea behind this reparameterization. And of course, like a lot of articles talk about it. So I would encourage you to go and look at the picture of like H being non-parameterized and then like reparameterized. Like what's the difference between both of them? Because like I, for some reason, have lost track of that. Okay, so that was like the introduction to variational autoencoders. And we are going to look at more stochastic autoencoders, and in fact, a similar idea next time when we talk about these models called GANs. So what we do is like, we did something similar here as well, that we had some input distribution, we learned that, and then you're producing something new as well, because that distribution that you're sampling may produce new points as well, right? So we are going to continue talking about that idea. But before that, a few applications of autoencoders. And the first one is recommender systems, of course. And the fundamental idea all these articles like talk about in detail how autoencoders can be used in recommender systems. But let me show you the main problem that we deal with when we are working with recommender systems. And I'll just show you like one small example, and then like maybe we can end. What happens in recommender systems, like whether you go on Amazon or Netflix, we have users and we have items, right? And so there are different ways of recommending things to users. And one way is like user-based collaborative filtering. Okay, so how does that work? Well, you'll have like, let's say user 1, user 2, user 3, right? And then you'll have like item 1, item 2, item 3, and so on, right? And then let's say user 1 rated something. So they are rating these items or like, I don't know, IN, and so on, right? And so this user also rated some of these items. And then this user also maybe rated, or maybe they did not rate. Now, my problem in a recommender system is that they haven't, like user 3 hasn't seen item 3 yet, right? So what would be the predicted rating for like this item for this user, right? So high level, what we do in recommender system problems is that I'll find, and this is like, by the way, user-based collaborative filtering. There are other techniques as well. So I'm just looking at this problem for the time being. Okay. So one way of doing that is that I'm going to find users who are very similar to user 3. And the way I can find the similarity of like user 3 with other users is maybe I use KNN. Let's say I use k nearest neighbors and find like some n number of neighbors, right? And then I decided that my similarity measure is like cosine similarity, right? So I use cosine similarity between user I and user 3, right? And so the way I'm going to predict this rating for like this user is that I'm going to find the sum of all these similarities, and I'm just like calling it SIM. It could be anything, right? With all the I users who are there, like who are nearest to this user and this user number 3, and multiply the responses of all those users as well, right? Whatever those like ith user responded for that item and so on, right? And divided by like the sum of all the similarities, right? So divided by that, and that's my predicted response for this user. Now, as you can see, this like high level process of getting the similarity, getting the sum, getting the response, it's all based off of like how much data I have for other users. And the issue in recommender systems is that usually this matrix, this user item matrix is sparse and extremely sparse, that like most of the users never go and like rate anything. Like I, at least for some reason, never go and rate anything on Amazon. So like maybe I'm adding to that problem. But like just like generally speaking, these data sets have that issue. And so one way of like dealing with them is that you perform some kind of matrix factorization and you go to the lower dimensional space and extract some useful information. That's one. And then the other way out is that you can use autoencoders. So that we've seen that it is going to extract useful information from some sparse matrix. It's easier for them and then reconstruct it. Maybe if you're using variational autoencoders, I can even get a more smoother output in the sense that it's going to even create some of these ratings. So that's how it's helpful. And also, like there is a cold start problem. I've provided an article for that in recommender systems that like new users coming in, we don't have any way of like figuring out what like similarity does this new user have with other users because I don't have their attributes. So then again, autoencoders come in and they help us like resolve that issue up to a certain extent because using that information, I can construct things, right? So that's why these are like very popular in recommender systems literature. And I would highly recommend using like reading this paper that's like solving cold start problem in recommendation with attribute graph neural networks. And as far as I remember, this talks about variational autoencoders. And so here is the overall framework. I think here it is. Yeah, so they are using like a variational autoencoder where you have like some input. You're trying to learn the mean and the standard deviation of like my input, right? That's what this is. And then this is the Z, which is like my latent representation Z, because this Z will be defined from my mu and my sigma, those vectors, right? And then this part is sometimes known as generation because you're sampling from that distribution and then you're creating some output. So that's exactly what they're doing here, generating preference embedding from attribute distribution. This is a very good like application of a variational autoencoder. And also one thing that I wanted to point out here is that like look at this overall structure here, that you have an input and then you have some kind of a generator, not a decoder, but a generator in some sense. We are going to use that a lot when we start talking about GAN models starting on Friday, that we can generate new output from my distribution of my input. That's why they're calling it this thing as generation in some ways. Okay. All right, yeah, so that's that. And the final one is this deep learning autoencoder for collaborative filtering. So I just talked about collaborative filtering. They're using a deep autoencoder to get better results in collaborative filtering, given the issue of like sparsity of data in collaborative filtering. So this is again a very good. So this is like the input, as you can see, is pretty sparse. And then they try to they use different combinations of encoder decoder combinations, and then produce different types of outputs sometimes for these sparse input data, and then they also show how deeper networks can produce better outputs, right? So if you keep increasing the depth, how they can get better results. That's what this paper talks about. And then these are the comparisons with different different depths, different non-linearities, and how can you improve the performance once you do that. Okay, so yeah, that's that. Yeah, so I think that's it from my end for autoencoders. So this was just an introduction to autoencoders. As I said on Friday, we'll talk more about these kind of networks where we are working with unsupervised learning problem, and we are trying to produce or generate new outputs based off of the input that we have. Right, so any questions, doubts? So that's it from my end. Yeah. People who are online, if you have questions, you can put it in the chat. Okay, then, thank you.